Hi everyone, today's lesson is going to be 1.2 characteristics of polynomial functions. I'll try to keep it short, but if I'm going too fast, I'd actually rather you listen more and try to understand the pattern as we have established in previous lessons, rather than you focus so much on copying down how to make these notes that you miss the actual point. As you know, because this is a video, you will find a link to this on Brightspace, so you don't have to worry too much about copying everything and having me slow down. The lesson is going to cover a recap of what we have established so far, of what a degree of a function tells us, what the leading coefficient tells us. Then we're going to try to marry that information with what I asked you to review yesterday, which was if you know the x-intercept of something, and know how to translate that into an equation and the connection between this and the brackets that you see for a quadratic, you're halfway there. Okay, so let's establish recap. What does a degree of a function tell you? Well, a degree of a function tells you whether it's going to go from quadrant 2 to quadrant 1, or if it's going to go from quadrant 3 to quadrant 1, right? If the degree, the largest degree, is even, then it's going to stay on the same side of the x-axis on the top. If the degree happens to be odd, the largest degree is odd, then we are going to have something from one side of the x-axis and moving on, crossing over into the other side of the x-axis. Okay? So what does the leading coefficient tell us? Well, the leading coefficient can tell us that if it's a negative, it's going to have a vertical reflection. It's going to go from 3 to 4 or 2 to 4. That's what we've established so far. Okay, well, that tells us where a curve is going to come from and where a curve is going to go, but it still leaves us very much to be desired about what action, like what the action-packed part in the center of this Cartesian coordinate is going to be. We have no idea whether it's going to be something like this, or just something like that, or whatnot. So what else could we take from an equation to help us visualize the graph more quickly, more efficiently, and of course, in university, be a part of the conversation, okay? I want you to consider a quadratic function, okay? So consider f of x equals ax squared plus bx plus c, with no numbers, just that. Quick pop quiz, what are the end behaviors for that function? Well, the degree is 2, so it's going to go from here to here. You guessed it. All right. And please also know that this equation, were learned so hard in grade 10 and of course grade 11 that factor form can be written as x minus s, right? And these numbers are very special. In our prerequisite skill, we talked about this. We call these the x-intercepts, okay? We can also call them the zeros, right? Or to make the equation equal a 0 itself, we can also consider them as roots. Now, whatever word you want to use, it's fine, at least for now. Okay. What would that look like? So let's get some examples down. I'm going to have 3 going. The first example is something that you already know. Let's draw a smaller graph. How about -1 and a 3? If my parabola looks something like this, with a -1 and a 3 as my x-intercepts, I know the function is going to be f is some kind of a value, x. You know what? Let's keep everything on one side. Sorry if you drew this already. I'm going to do 1 with a 3. Let's do that instead. Okay. So if that is the case, we automatically know that within this factored form, the brackets must involve a subtraction of a 1 and a subtraction of a 3. Okay? Why? Well, we know that if x equals a 1, then plugging 1 into the equation, my answer is going to be a 0. If x equals a 3, plugging in a 3 into the equation will give you a y value of 0. Right? So we have two distinct numbers that will give you a y value of 0. We call this scenario two distinct or different roots. Okay. But of course, you know from your experience, that's not the only kind of parabola we can get. We can also get something like this, where there's only one x-intercept. Well, I still have to have an equation for that, but there's only one x-intercept. So how do I create two brackets with x multiplying with each other, but only one number allows this equation to equal a 0? Well, that means both brackets must be identical. Here, we have a scenario where one bracket squared makes the curve touch the x-axis just once. Okay? And just to establish or continue the pattern from the right example that we just had, we call the scenario two equal roots. Why do we say two? Well, we have two brackets here, right? We have two situations where the y value will become a 0, but they happen to be the same, so they are equal. So we call it two equal roots. And lastly, if a parabola could have two x-intercepts, or if I move it up, it could have one x-intercept, I can move it up further to a scenario where I have no x-intercepts. What does that mean for the equation? It means that the equation cannot be factored. There's no situation where I could turn that into two brackets multiplying with each other. It is not factorable. And if it's not factorable, there are no x, well, being not factorable, and it would have no x-intercepts or zeros or roots. Okay. So before I move on, since we're doing this as a recap, I'll quickly add a little note to this. Therefore, if the degree, and I'm going to use the variable n, if the degree n happens to be 2, then how many x-intercepts could I have? The number of x-intercepts, or the number of zeros, could be less than or equal to 2, but also greater than or equal to 0. It has to be 0, 1, or 2. Okay. Also note how many minimums or maximums I have. If the degree is a 2, in other words, if it's a parabola, there is only one possible minimum or one possible maximum. I'm going to introduce a new word. Instead of calling it max or min, I'm going to call them extremes. Okay, so I'm going to say also note extremes. Okay, which means max or a min. Local max, local, whatever. If the degree is n equals 2, if n equals 2, then I only have one extremum, singular for extremes. Extremum. All right. And of course, I don't have to say anything about the a value being negative. If the a value is negative, obviously it'll be upside down. If the a value is negative, it would be reflected this way. If the a value was negative, it'd be something like that. Okay, but I'm not going to talk about that. Okay, so this is something we've learned in grade 10 and grade 11. Let's push it now. Why would this information help us visualize a graph better? Okay, so if you understand this, I'm going to push this example and I'm going to ask you to consider not a quadratic, but consider a cubic. Here we go. If you need more paper, you might want to, get a new one out. Okay, here we go. Consider a cubic function. And one example would be ax to the power of 3 and bx to the power of 2 plus cx plus d, some random constant. Okay? If a cubic function, if I told you that a cubic function here was factorable, what would the factored form look like? Well, think about a pattern. If the exponent was x to the power of 2, we needed 2 brackets multiplying with each other so that the x times x, it becomes x squared. If the largest degree is a 3, where did my thing go? There. If the largest exponent is a 3, then I think you will agree with me in that there would potentially be 3 different RST, 3 different brackets multiplying with each other. Does that sort of make sense? Right? I hope you can believe me, right? X times x, this part would give me x squared minus something, and something. And this would be x minus t. And if I continue multiplying through x squared times x, I will get some kind of x3 as my final answer. Okay? So just, even if you don't quite get it, believe me in saying that if I can factor a cubic, it would look something like this. Now, look at our example for quadratic, and tell me what 2 brackets means versus 3 brackets. If I have 3 brackets, how many x-intercepts would that represent? Okay. Right. If I have 3 brackets, what would these numbers represent? Also, if n equals 3, going back to what we know before, if the degree n equals 3, what does that tell you about the n behaviors? Let's piece that together. If the degree is a 3, I know that I'm coming from here. I know that I'm going to here. And somewhere along the x-axis, I'm going to have 3 x-intercepts. With these 5 pieces of information, can you vaguely sketch what the graph could look like? I hope you could. Like, it would come up here, it would pass through, and because it has to pass through this x-intercept, I have to flip over sometime and go through. And because I have to go through this x-intercept, at some point, it has to curve over and go back up. It's going to look something like this. So if I know the x-intercepts, it gives so much information of what the graph could look like near the center of the curve. So let's do it as an example, okay? So I'm going to just do this, tidy it up a little bit. It's going to look something like this. So let's, for example, let's pretend that's a -2, that's a 1, and that's a +4. What would this equation look like? Well, it will be some value a, x plus a 2, x minus a 1, and x minus 4. We have 3 zeros. Right? So we have a lot more information. And if I give you a test question in factored form, you can give me a pretty accurate sketch. But just like a quadratic, remember, When the degree was a 2, I could have 2 x-intercepts, but I could also have 1. So if the degree is a 3, I could have 3 x-intercepts, but could I have 2 or 1 or none? Let's investigate. Okay. Can it have less than 3 zeros? Yes. Yes, it can. Okay. Can it have less? Sorry. Can a cubic function have less than 3 zeros? Yes, it can. But how? Well, let's talk about it. As an example, let's pretend I have a -2 here, and in between there is a 3 here. Because it is cubic, I still have to go from Q3 to Q1. Okay. But how do I go from here and end up here when I have only 2 points to touch? Like I can't do, and that, because then I cross the x-axis again. The question just told me that I don't have that luxury. So how would you do it? I'm going to ask the substitute to pause the video and give 30 seconds. Have some time to think creatively of how that might be possible. And pause. Did you try it? Here is one way we can make this happen. From Q3, it goes through this x-axis, and then, just like the parabola, it just touches. This portion here, it behaves like a parabola that has 2 equal roots. So I'm going to say this is 2 equal roots. It just touches. So the equation could look something like x plus 2, and then x minus 3 with another x minus 3. Or x minus 3 squared. So x minus 3 squared. Focus on this section right here. I'll raise this up. Focus on that section right there. Doesn't that look like a parabola that touches just at 3? Yeah. At that location, the curve will behave like a parabola. And that's it. That's what it's going to look like. What is another example? How else could I draw a curve that has -2 and a 3? Well, what about I have here, oops, that wasn't very good, here and there. And between these two, which one is the x-intercept that behaves as if there were 2 roots? Right here, that's 2 equal roots. So my equation would look something like x plus 2 with another x plus 2, and then x minus 3, or a x plus 2 squared, x minus 3. This portion right here, the curve behaves like a parabola, just touching once and moving on. Okay. So you just have to watch out for that. There are some ways you can go about making these curves, I guess, possible. Could a cubic function have less than 2? Okay. Can a cubic function have, so less than 2, so can it have 1 0? Yes, yes it can. It still has to go through Q3 to Q1, but it only has one x-intercept. So for example, what if we have the x-intercept, let's pretend it's a 1. How do we go from Q3 to Q1 and only go through a single location? Pause the video and give you 30 seconds. Go. Did you think about it? It could be a couple of different, 3 different ways. We could have something like this. That portion behaves as 3 equal roots. That is, it behaves like a normal cubic function. It's going to look something like this. F of x is equal to x minus 1 times x minus 1 times x minus 1, which is x minus 1 cubed, right? And you've seen this in grade 11, where you had to explore transformations of cubic functions, right? It looked something like this. However, what else could we have? We could have something like this, and we'll get to it. We could have a situation where one part isn't factorable, so they don't have a x-intercept. Maybe we can also have something like that. Okay. And this doesn't behave like a parabola. This doesn't behave like a cubic. The line or the curve goes through that x-intercept as if it was a linear, like a straight line. And so I know that this equation is going to have, let's see, the 1 and something else here that doesn't allow us to equal a 0. Here, same thing. F of x is equal to x minus 1 multiplied by something that doesn't allow it to equal a 0. You might be asking, how does it not equal a 0? Well, maybe it has something like 2x squared plus x plus 100 or something like that. No matter what number you plug in for x, you will never get this to equal a 0. Okay? In any case, what I was trying to establish is, once again, if you know what the x-intercepts are, or even if you know how the line curves through it, you have a lot of clues to work with on how the curve might appear. Okay? So let's establish a rule. In this case, we have if the degree n was 3, we know that the number of x-intercepts was 3 or 2 or 1, but never a 0. And I'm wondering if you can figure out why it would always have at least one x-intercept. We'll cover it when I get back, okay, when we get back together on Monday. But if the degree happens to be a 3, then the number of zeros could be a maximum of 3 and a minimum of 1. Also, note the extremes. How many extremes or how many maxes or mins could I have? I could have 1, 2. I could have 2 max and mins. I could have 2 max and mins. I could have 1, 2 max and mins, 1, 2 max and mins, or I could have none, no max and mins. Okay, so if the degree is 3, I could have the number of extremes be a maximum of 2 and a minimum of 0. So it's starting to look a little complicated, and you're wondering, how much of this do I have to memorize? You don't really have to memorize per se if you understand where these numbers are coming from. But generally speaking, if you want to take home a kind of formula, I'll leave you with this. By definition, for even, okay, versus odd n degree. For zeros, it's always going to be the number of zeros being a minimum of 0 and a maximum of whatever the degree number is. For odd functions or odd degree functions, where did I put an E there? You could have a minimum of 1. It's got to cross the x-intercept at least once. And the maximum is, again, n. For extremes, at most, or at least, at most, it's going to have, for even degrees, 1 less than whatever the degree is. So how about I just write this down? The number of extremes is, there must be at least 1 hump and a maximum of the degree minus 1 hump. For odd, the number of extremes is minimum of 0. It doesn't have to have an extreme, but the maximum is n minus 1. So if you want to memorize it, maybe you could think about how this is 0 and 1. This is 1 and 0. Everything else is the same. Not sure what you can develop to help yourself memorize that, but there it is. Around this time, I'd be asking, hey, do you have any questions? But I'd like to see just how much of this you're able to pick up. So I'm going to ask the substitute to pause the video. I want to ask, can you sketch roughly all the possibilities of a quartic function? That is, the function is going to look like a 1, 2, 3, RSTU, 4. A quartic function that is factored in this way. Can you sketch all possibilities, all the x-intercepts and what it might look like for a quartic function? Okay, if the substitute could pause the video, let's give the students about 5 minutes and people can bounce ideas back and forth and I will sketch them all when we reconvene. Yeah, 5 minutes, go. Okay, I'm going to get going. So if you had a quartic function like this, C, D, and E, okay, you could potentially have all 4 x-intercepts be completely distinct. And I would know that it comes from quadrant 2 and goes to 1. It could look something like 1, 2, 3, 4. Something like that. That would be the most basic. Sometimes you might have 3 x-intercepts. Let's see if I could draw it a little smaller so I can fit them all here. 1, 2, 3. I have to still start from quadrant 2. Okay, so how about I do something like crossing? And instead of actually crossing, I could pretend that this middle one serves as a equal to equal roots. So it could look like that. And I have 3 x-intercepts. What if I make this x-intercept serve as a, serve as a 2 equal roots? Then I could have something like that. I could also make that third x-intercept be the one that is the equal roots. So it would go through like a straight line, go through like a straight line, and then it would touch like a parabola, and there we go. So again, as an example, maybe this is a -2, that's a 1 and a 3. That would look something like x plus 2 bracket with x minus 1 with another x minus 1 with the x minus 3. For this one, the -2 is my two equal roots. So we have x plus 2 with another x plus 2 with the x minus 1 and an x minus 3. For the last example, the x equals 3 is the x-intercept that serves as two equal roots. So this would be x plus 2 times x minus 1 times x minus 3 times another x minus 3. So it would look something like that. So though there's three different examples we could have for three x-intercepts, what if I said there were only two x-intercepts? It would look like it's going to be a lot of possibilities. I'm not going to go about doing the equation for all of them, but I'll do one. Let's pretend that's a -2 and that is a 2. Okay. Starting from quadrant 2, finish at quadrant 1. It could be something like touch, like it was a parabola, two equal roots, and touch, like a parabola, two equal roots. It would be x plus 2 times another x plus 2 times x minus 2 times another x minus 2. If the -2 here is just a distinct root, maybe it goes through like this, and then it behaves as a triple. How do I know it's a triple? Well, there are no other x-intercepts, and I have to go through here, right? So this would be x plus 2, and this would be x minus 2 times another x minus 2 times another x minus 2. It would look like that. So that exponent sort of shows you what behavior the curve will take near that x-intercept. The same way, what if the second one here, what if the x equals -2 was the place where it was 3 equal roots, and the value of +2 was where we have a single x-intercept? It would probably look something like goes through as if it was cubic, and then goes through as if it was singular. So the behavior near x equals -2, x plus 2, it behaves like a cubic because we have 3 of these multiplying with each other, and here is just x minus 2. Lastly, this one doesn't have 2, it would have 1 x-intercept, something like that. Well, it has to come from here, it has to go from here, and it also has to have 4 brackets because this is quartic. How do I do that? Well, it's going to behave something like this with a really wide bottom. It's going to look something like that. This is 4 equal roots, x plus 1 times x plus 1 times x plus 1 times x plus 1. It's going to be something x plus 1 to the power of 4. I think we got it all. And as you can see, it starts getting really, really, really out of proportion here. There's so many things to consider. So another shameless plug, you're not to memorize what quartic looks like. Like, what if instead of quartic, I asked you to do quintic? In other words, power of 5. The goal is not to memorize what quartic or quintic could be and all its possibilities. Your goal is to understand what the x-intercepts tell you, or rather, what the equation tells you about the graph. And if you have a graph, what does that tell you about the equation? Okay. Along with what we learned here, the zeros versus extremes, let's quickly recap what we can establish. If the equation is given to us in factored form, we immediately know what the x-intercepts are. And here's the important part. If you got lost in this entire lesson, remember this. If you take a look at how the curve behaves at the x-intercept, it gives you a really good idea of whether the factor or the bracket is going to have a power of 1, a power of 2, a power of 3, or a power of 4, so on and so forth. Okay, the graph gives a very good idea of what the equation is. The equation gives a very good idea of what the graph is. And this is another big step towards being able to have a quick conversation about math with people at your level in university. Okay. For weekend homework, I'm going to ask you to take a look at the textbook questions, the sheet. Questions 1 to 3, don't do triple I, just do 1I and 2I. Numbers 5 to 7, 9, and 12. Any questions that have the word symmetry on it, ignore. Okay, I'm going to go into some algebra of symmetry when we come back later. Another reminder that Wednesday is a mini test. Okay. You need to practice. The concepts, really, if you get the hang of it, it's not hard, but it's a lot of material that you need to consider all at once and sort of keep in your brain so that you really check off all the things in the checklist at once. Okay. On Monday, I'll go through practice. We'll do some harder examples, cover any questions you might have. Email me if you need to as well. And when we get back together, I'm going to introduce a fun, but essentially what I'm going to say, relatively useless formula in your math career. But it's something that sort of helps and brings together our little thing on finite differences. Okay. If you take a look at our formula sheet that I gave you earlier in the week, you might see for the very first time, on the very top, I mean, a finite difference is equal to something that looks like this. Once you get a hang of this and practice all that, I am going to introduce what this formula does for you. It's a bit of a fun fact kind of formula. It's not very helpful in university, but we're going to cover it. Okay. So once again, quick homework, try the textbook questions, homework, practice for the mini test. And when we come back on Monday, I'll take up any questions you have and also introduce a times and factorial, what this weird formula is. Okay, I know that was a lot. If you need to revisit the video, go ahead. I will hopefully wish you a good weekend and see you healthy and ready to go on Monday. Okay, have a great one.